Now, that's how you do configurations or spin orbital configurations for atoms. What if you had a diatomic molecule? That'll be the simplest entry into the world of polyatomic molecules. We'll stop at diatomics and look at those for a minute. Well, your atomic orbitals are going to combine to form molecular orbitals, whether it's a diatomic or a polyatomic. But it's easier to see here for diatomics. In fact, to make it even easier, let's assume the two atoms in the diatomic are the same atom. So those are called homonuclear diatomics. So H2 or O2 or N2 or F2, that kind of thing. Let's look at those. When I combine my atomic orbitals to form molecular orbitals, there are various ways this can happen. So let's go through all the possibilities for a homonuclear diatomic. So I'm going to have nucleus A and nucleus B, and each one's going to have an atomic orbital on them, and I'm going to say how did those atomic orbitals combine? Because it's homonuclear, the orbitals will have the same size. If I pick the two 1s's or the two 2s's, they're symmetry equivalent. So suppose I get a s orbital on the nucleus on the left and an s orbital on the nucleus on the right, and again they're identical. I can make plus or minus combinations of these. So let's take a plus combination. Well, then I get constructive interference if these two spheres overlap. I haven't drawn them here as if they overlap, but imagine they might overlap to some extent. Then I can get constructive interference and the spheres kind of merge into each other, and I get this kind of blob. And the bond axis runs down this way because, again, there's a nucleus at the center of this and a nucleus at the center of that. So if I connect those, I get a bond axis here. And if I were to look down the bond axis, I would see that it's cylindrically symmetric. Okay? So it's the same if I go up or if I go down or go to the left or the right. And cylindrically symmetric orbitals are called sigma orbitals. And this one also has an additional subscript on it. I'll call that a G. This is German for gerade, which means even. And it's even with respect to inversion symmetry. So if I started at the middle, which would be somewhere here, and if I were to go left or right, it's the same. If I go up or down, it's the same. So going the same in every direction, if I start from the center, means it's a gerade or even orbital. That's the plus combination. There's a minus combination. So now imagine I take this red orbital on the left and I subtract a red orbital on the right. So subtracting an orbital would be the same as adding one of the opposite sign. And here let me use red and blue to be the two signs. You could think of red as positive and blue as negative, or vice versa, it doesn't matter. So minus a red orbital or add a blue orbital. If I add an opposite sign, then any place that they touch or have a little bit of overlap with each other will cancel, because on the left I'll have some red orbital and on the right I'll have some blue orbital, and they cancel out and they go to zero. So smack in the middle, there's no amplitude to my orbital. And in fact, I get an angular node here. And then on the right, I get the blue phase, and on the left, I have the original red phase. Now, if I were to look down the bond axis, so imagine I'm standing over on the side of this thing looking down the bond axis, then again, it's cylindrically symmetric, because top is the same as bottom and left is the same as right. So it is cylindrically symmetric, so it is a sigma orbital. But now if I go, if I start at the middle and I go one way, I get one phase. If I go to the left, I get a red phase. But if I go the other way, I get the opposite phase. So now with respect to inversion, or respect to the center of symmetry, it's anti-symmetric as I go one way or the other way. So it's an ungerade orbital, or sigma u. And furthermore, I'll put a star on it just to notate that it's an anti-bonding orbital. Anti-bonding orbitals are ones where if I start walking from one nucleus to the other nucleus, I get a sign change. And that certainly happens here. If I start on the left and go towards the right, my sign changes halfway in between. So it's anti-bonding. This would be a bonding orbital because if I go from the left to the right, the phase stays the same and I get some nice constructive interference that stabilizes that orbital. So I think I just walked through this. If you have constructive interference as you go from one nucleus to the other, like I do here, that's a bonding orbital. And if I have destructive interference that causes a sign change as I go from one nucleus to the other, then that's an anti-bonding orbital. And the star typically will mean anti-bonding if you put it on an orbital label. Okay? Now, that's how you combine a couple s orbitals, either in phase to make a bonding orbital or out of phase to make an anti-bonding orbital. They're both sigmas. What if I combine p orbitals? Well, it's going to depend on which way around the p orbitals are pointing. So let's take pairs that are pointing the same way as each other, and let's say that I take a pz orbital on one atom and a pz orbital on the other atom. And if we call the internuclear axis z, then it means that these p orbitals are the ones that are pointing along the bond axis, okay? So here on the left, I've got a pz orbital. It's pointing in the direction of the bond axis. Here on the right, centered at the other nucleus, I've got another pz orbital. And these guys, if they're close enough to each other, they will overlap in the middle. Here I've put the minus combination up front because I think it's easier to visualize this one first. So let's subtract the right one from the left one. Well, subtracting is the same as adding the opposite phase. So if I change the phase on this, this blue lobe turns red, and this red lobe turns blue. So I'm adding a red lobe here to this red lobe where they overlap, and so I get red in the middle, constructive interference. On the left, nothing happened to this guy, so he just kind of comes along. And on the right, nothing happens to this guy. Now it's minus, so the sign's different. So it's blue over on the right, and that's the combination. Now if I look down the bond axis from the side, then I see that it's the same up top or on bottom or left and right. So it's a sigma orbital again. This guy's cylindrically symmetric, looking down the bond axis. It's bonding because if this is the nucleus right here, where I get a sign change in my p lobe, so the nucleus would be in the middle. So here's my nucleus. If I start at this nucleus and walk towards the other nucleus, I don't change the sign. And here I end up at the other nucleus, and I didn't have to change the sign. This other lobe's on the other side of the nucleus, so that doesn't count. So it's constructive interference between the two nuclei, and so therefore it's a bonding orbital. It's a Garada orbital, because if I start smack in the middle, and I go right, I see red, and then I see blue. But if I go left, I see red, and then I see blue. I see the same thing in both directions. So it's even, it's Garada. Now, what if I add these two? Well, now I get destructive interference between this red lobe and this blue lobe, so they cancel each other out, and smack in the middle, I get nothing. I get an angular node. Then, to the left, I wind up in parts of this that didn't destructively overlap with parts of that, so I get a little red piece, so that's this. And then further on to the left, I get a blue piece, that's this. And then similarly, if I go to the right, then I hit the remainder of this lobe that didn't cancel out with that. So there's a little blue piece that starts here, and I show it there. And then this red piece kind of just comes along, so he's there. And it, again, is cylindrically symmetric if I look down the bond axis, so it's sigma orbital. It's anti-bonding, because if I go from one nucleus, which I guess starts around here somewhere, and I go across, then I have a red phase, but then I have a blue phase, so I get a sign change going from one nucleus to the other nucleus. So it's anti-bonding, and it's ungerada, because if I go left, I see blue, red, and then blue, but if I go right, I see blue and then red, so it's opposite, so it's ungerada, it's uneven with respect to the center. Okay, that's how you combine two pz orbitals that are along the same axis, pointing kind of head to head or head to tail. What about p orbitals that are like perpendicular to each other? So they both point in the same direction, but they're not pointed at each other. Okay, so like px and px. So here's a p orbital, there's a p orbital. What if these guys overlap? If they are close enough to each other and they blend into each other a little bit, then these two red lobes give you one big red blob, and the two blue lobes give you a big blue blob. And this guy, if I look down the bond axis, is he cylindrically symmetric? No, because if I look up, he's red, but if I look down, he's blue, and that's not the same. It does a 180-degree sign change. It goes from positive to negative, or vice versa, as I rotate around, looking around the bond axis. And so that is called a pi orbital. Or if you like, you could say that there's an angular node that runs through the bond axis. So there's a pi orbital because of that. Now, if I were to subtract instead of add, well, what does that do? Well, the part on the left stays the same, but the part on the right changes sign, and so I get this guy, and then any place they might have touched, they wind up having destructive interference and canceling each other. So there's nothing smack in between the two nuclei. So there's an additional angular node there. But again, if I look down the bond axis and I think about going around the cylinder that I would have if it was a sigma orbital, now I get one sign change, blue to red or vice versa. And so one sign change makes that a pi orbital. And is this one Ungurata or Gurata? Well, it's Gurata because if I start in the middle and go one way, let's say diagonally up this way, it's blue, and if I go the opposite way, that would be diagonally this way, it's blue. So it stays the same if I go in the opposite direction. So that's even, or Gurata. It's anti-bonding because if I start at one nucleus and go across to the other one, I have a sign change. Well, if I stay exactly on the bond axis, I actually don't have any orbital at all because it's a pi orbital. But if I were just a tiny bit up or a tiny bit down, and I go from one nucleus to the other, there is a sign change. So it's anti-bonding. It's destructive interference between one nucleus and reaching the second nucleus. So there we go. There's a couple molecular orbitals that come out. And my slides have been saying this, I haven't been pointing it out, but in every case, if I take two atomic orbitals and I do a plus combo and a minus combo, then I get two molecular orbitals out. And that's a general feature. Anytime I combine two atomic orbitals, I'll get two molecular orbitals, or if I were to somehow combine three atomic orbitals, I'd get three molecular orbitals. So I have a conservation there. The only time the number of molecular orbitals in a calculation wouldn't equal the number of atomic orbitals is if there were some linear dependencies in your basis functions that I were to toss out, in which case the number of molecular orbitals would be lower. But at an intro level, we expect these numbers to be the same. Now, py and py, it's the same story as px and px, it's just everything is rotating 90 degrees compared to what I did a minute ago. So I think you can see these guys, again, have constructive interference, and it's not cylindrically symmetric. There's a sign change, so it's a pi orbital. This one is a pi u, because if I go in one direction, I have a certain sign. If I go in the opposite direction, I have another sign, so it's Ungurata. And then the minus one, it again gives me this four-lobed thing, and again, it's Gurata with respect to the middle. And it's anti-bonding because I switch sign if I go from one nucleus to the other. So these two pictures are identical to the previous two pictures. They're just rotated 90 degrees as if they're coming out of the page at you. Okay, now let me do something cool with all these orbital combos we've been looking at. What I'm showing you now is a molecular orbital diagram for a homonuclear diatomic molecule. On the left are the atomic orbitals for atom A on the left, and on the right are the atomic orbitals for atom B. And you can see, because it's homonuclear, the left and the right atomic orbital patterns are identical to each other. In the middle, I'm showing you how these different orbitals combine when you take plus and minus combos to give you molecular orbitals. And by symmetry, the combos are exactly plus or minus. If it was a heteronuclear diatomic, the combinations could be more complicated, and the things on the left wouldn't exactly match the ones on the right. But for simplicity, let's talk about this one. So we've kind of already talked about how things combine, so it should be easy to understand this. Your 1s orbitals can combine in phase to give you this orbital, which is Gerada. Here I'm showing it not quite as the blob I showed earlier, because I'm imagining the 1s orbitals, they're very tight functions, they're very small, if you like. And so in the diatomic molecule, the nuclei may not be close enough for these 1s orbitals to overlap very much. Now, of course, they have some small overlap. They're not literally spheres the way I'm drawing them in a cartoon here. But you could imagine that the regions where there's maximal electron density don't overlap very much. So I've drawn it here as two separated spheres. What I actually did is I used WebMO and generated actual molecular orbitals and plotted these diagrams using an ISO value for the electron density. So these are ISO surfaces. There is a little bit of density that leaks out, to further regions that we're not showing. But these are ISO surfaces depicting the molecular orbitals. Of course, then you can have a negative combo of these, and so this one's anti-bonding. And we just number them. This is the first sigma G. This is the first sigma U star. Then if I go up to 2s, you see this orbital is bigger than that one. So these guys are more likely to overlap with each other. So this gives me the second sigma G orbital. It's a bonding orbital. It's cylindrically symmetric. This gives me the second sigma U star orbital. It looks basically like this one. It's just bigger. And then my p orbitals, I got 3 on the left, 3 on the right. I have 3 pairs, and I can do plus or minus for each pair. So 6 AOs go in, 6 MOs come out, and if I take the 2 PZs that sort of point at each other, then I get this guy. This is the third sigma G orbital that I've encountered. 1, 2, 3. It's bonding with respect to the nuclei. Remember, the nucleus is right on the edge between blue and red here, and on the edge between blue and red there. So the sign doesn't change as I go from one nucleus to the other. So it is bonding, and it's Gerada. And then the p orbitals that are perpendicular to each other, I can form a pair that gives me either this guy, this is bonding, or the 90-degree rotation of that guy, which is bonding. And the other combinations then give me these. So if I take the 2 PZs and combine them in a way that's bad and get destructive interference in the middle, then that gives me the third sigma U star orbital. It's anti-bonding. And if I combine the p orbitals that are perpendicular in less effective ways, I get anti-bonding orbitals that look like this. And again, this one is the same as that one. They're just rotated 90 degrees from each other. And because these guys have the same energy, they're just rotations of each other. That's another reason they're a pi orbital. Pi orbitals come in pairs, and each member of the pair has the same energy. They're just, one's a rotation of the other one by 90 degrees. So that's true here, that's true here. These have the same energy, one's a rotation of the other. The only caveat to this is that the order of these orbitals can change depending on which diatomic molecule you're talking about. So if you have like, N2, then it's actually the case that the pi orbital is below the third sigma G orbital. So when you reach the O2 molecule, if you had O2 or F2, then it's the way I've drawn it. But if you're before that in the periodic table, like N2 or C2, then actually this pair of pi orbitals is below the 3 sigma g. So that's just a little quirk to keep in mind. So let's talk about the Aufbau principle and how it works for diatomic molecules. So here I'm showing a portion of the microorbital diagram. This will suffice for my first example or two. Suppose I have H2. Well, each hydrogen, if I had a single atom, would have 1 electron. So I'm going to draw that with a little up arrow on the left to denote the electron in this 1s orbital for this hydrogen. And then the hydrogen on the right gets 1 electron, so I'll put a little up arrow there. And then that helps me count. So I've got a total of 2 electrons. Where do I put them? I put them in a molecular orbital, and I use the Aufbau principle to fill up starting with the lowest energy orbital. And the lowest energy orbital is this 1 sigma g. So it gets 2 electrons, because they've got 2 electrons to work with. So there they go. And then what's the electron configuration of this? Well, now the labels of the orbitals are things like 1 sigma g. They're not s or p or d or anything anymore. So I'll just say 2 electrons go into 1 sigma g, or 1 sigma g2. That's it. Now, how many bonds does H2 have? Well, if you remember any freshman chem at all, you remember H2 has 1 bond. Okay? And hopefully that makes sense. There are 2 electrons. There are 2 electrons that could go into a bonding orbital. This is a bonding orbital. So if a bonding orbital gets 2 electrons in it, that completes a bond and I get 1 bond. All right, how about something more interesting? What if I were to go to helium-2? Well, in this case, each helium atom has 2 electrons in it. So there's 2 there and there's 2 there. And then when these orbitals approach each other and start to form a diatomic molecule, they overlap, and I get this orbital or that orbital. And I've got 4 electrons to work with, so I just fill up starting from the bottom. So I put 2 electrons in this one, then I put 2 electrons in that one, and I get this. Now, how many bonds? Well, let me write down the electron configuration first. It's 1 sigma G2 and 1 sigma U star 2. Okay. Now, how many bonds is that? Well, if you remember any freshman chem at all, you remember helium-2 isn't a stable molecule. It turns out if you're a very clever experimentalist, you can maybe kind of make it as a really, really long bond length. But it's not a diatomic molecule. Helium likes to stay as a monoatomic atom. So in chemistry, if somebody asked you how many bonds are in a helium-2 molecule, you'd say, well, it doesn't form a helium-2 molecule, or there's essentially 0 bonds, and that would be correct. And would you guess that from this molecular orbital diagram? Well, maybe so, because I've got a pair of electrons in a bonding orbital, but a pair of electrons in an anti-bonding orbital. And you might think that kind of cancels out, and it does. And so that's why helium-2 doesn't really form a stable diatomic molecule, is because the anti-bonding character cancels the bonding character, and there's no stabilization to form this diatomic molecule. So it basically doesn't, except at ultra cold temperatures, and then only just barely. All right, we need to do another example. How about lithium? Just keep it easy for now. We'll add 1 more electron to each atom. Well, so now 3 electrons on the left, 3 electrons on the right. Aufbau principle says I fill up the molecular orbitals until I run out of electrons. So I can put 2 electrons here, 2 electrons here, and that's 4. I got 2 more electrons, so I can put them there. And that's what I do. So there we go, 3 pairs of electrons, 6 electrons went in, 6 electrons came out. And what is the electron configuration? 2 electrons in 1 sigma G, 2 electrons in 1 sigma U star, 2 electrons in the 2nd sigma G. And how many bonds are in lithium-2? Well, you may not know much about lithium-2, but if you do, you know it has 1 bond. And that kind of matches what you might guess from the MO diagram, because again, this anti-bond will cancel that bond, but now I have a new bond, and so I expect a net of 1 bond, and there is 1 bond. So cool, that seems to fit. Let me define a bond order. A bond order in this MO picture is basically the number of bonds, but I can calculate it from diagrams like I had a minute ago. All I do is I take the number of bonding electrons and I subtract the number of anti-bonding electrons, and I divide by 2 because remember it takes 2 electrons to form a single bond, and that's the bond order. Now you might notice in this formula it would be possible to have half a bond, because what if I had 3 bonding electrons and 2 anti-bonding electrons? Then 3 minus 2 would be 1, divided by 2, I'd have a half a bond. Is that crazy? No. It's perfectly fine to talk about half bonds. It just means you have a bond orbital that's half filled, and that is weaker than a full single bond, and that's a thing, and it's fine. So you can do that. Now, I need to do some more complicated examples because I'm not sure we still have the full picture. So let's go to B2, and for the sake of making this still visible, I've kind of chopped off the 1s orbitals, combining to form the 1 sigma g and the 1 sigma u star. That's kind of like below the diagram. Sorry about that, but that makes the rest of it a little bigger and easier to see. So let's do B2. Boron is the 5th element, so it has 5 electrons, and a couple of them go in the 1s, which I'm not showing, it's below the diagram, and then a couple of them go in the 2s, which I will show, and then I have one more to show in the 2p. So let's do that. Okay, so 1s electron's not visible, but the rest of it visible, so 3 valence electrons on each boron. And then I'm going to use the Aufbau principle to fill up the molecular orbitals. Well, I'll fill the 1 sigma g and the 1 sigma u star, which are again below the diagram, and then that'll take care of 4 of the electrons, and I'll have 6 electrons remaining, the ones I'm showing here on this diagram. Where will they go? Just start at the bottom and fill up until you run out. So here we go. 2 go here, bonding orbital, 2 go here, anti-bonding orbital, kind of cancels this bond. Likewise, the 1 sigma g and 1 sigma u star canceled each other out as well. And then I'm left with 2 electrons, and I use the Hund's rule to say don't pair them up, keep them unpaired, because these 2 orbitals have the same energy because it's a pi orbital. Put an alpha spin here and an alpha spin there. Now I've run out of electrons. Now I'm done. That's the electron configuration. You could write this simply as 1 sigma g2, 1 sigma u star 2, 2 sigma g2, that's this one, 2 sigma u star 2, that's that one, and then the 1 pi, you could write 1 pi ux1, 1 pi uy1 if you wanted, but for shorthand, sometimes people just say 1 pi u2 and kind of lump the pi u together and know that there's a pair of them. That's fine too. And how many bonds does this have? Well, the 1 sigma g and 1 sigma u star canceled, the 2 sigma g and 2 sigma u star cancel. I'm left with 2 electrons in bonding orbitals. Is that one bond? Well, maybe yes, maybe no. I mean, they're not paired, so it's not a normal sigma bond, certainly. They're not paired up. But my bond order formula, if I use it, everything canceled except these 2 electrons, and they're in a bonding orbital. So 2 minus 0 divided by 2 is 1. So there's a net of 1 bond. And because I already canceled these other guys. So yeah, you could call it one bond. Maybe you put it in quotes to mean it's a little bit of a weird bond, but still bond order of 1 anyway. And that's it for B2. How about C2? This is a fascinating one. There are now 2 more electrons, 1 more electron for each atom. Again, I won't show the 1 sigma stuff just to make it a little bigger on the screen. But there's my electrons. Now I've got a second p electron in carbon, and use the Aufbau principle, so fill everything up. So I've got 1, 2, 3, 4 electrons that are in the valence that I can see on each atom. So that's 8 electrons. So start here and then use up 8 electrons. So 2 go here, 2 go here, and then 2 go here and 2 go here. There we go. That's 8 electrons. 8 valence electrons shown, 8 valence electrons accounted for. The electron configuration then is 1 sigma G2, 1 sigma U star 2, 2 sigma G2, 2 sigma U star 2, and there are 4 electrons in the 1 pi U, and that fills it up. And my bond order formula would then tell me there are 2 bonds because all the lower stuff cancels. This stuff doesn't cancel. 4 electrons are in bonding orbitals. Divide that by 2, I get 2 bonds. This is super weird because, notice, for C2, the pi orbital is below the sigma orbital. I have 2 pi bonds, overlaps between p orbitals, pi bonds. They're perpendicular to each other, and no net sigma bonds. Isn't that weird? We always think we put a sigma bond first, and then we start putting on pi bonds if we have enough electrons. But in C2, it's the other way around. You start putting on pi bonds, and then I run out of electrons before I would have gotten to the sigma bond. So, very unusual bonding in this molecule. In C2, there's a very, very low energy gap between the 1 pi u and the 3 sigma g. Okay, finally O2, just because it's such a classic mistake for beginners of computational chemistry, let me do this one. I think you see how these work by now. Here's the electrons I have in oxygen atom. I've got 4 electrons that go in the 2p, so I'll do this version. I did the alpha-bow principle. I put alpha, alpha, alpha. Then I had 1 more, so I had to come back and pair it. Same thing on the right. And then I just filled these up until I run out of electrons. So if I count my electrons up, I get this. Same as C2 starting off, except that now I've filled the 3 sigma g, which is now hot below the 1 pi u. And then I have 2 more electrons, because O2 has a net of 4 more electrons than C2. I use the Hund's rule to not pair them. So I have a spin up and a spin up, and then I run out before I have to go back and pair anything up. Very interesting. So this gives, the stuff below cancels. This gives me 3 bonds here, but then 2 electrons partially cancel some of this out, and the bond order is a net of 2 bonds, because effectively 2 anti-bonding electrons cancel 2 of the bonding electrons, giving me a net of 2 bonds. And the configuration is just this that you see here. Here I've filled the 1 pi u, so it's got 4 electrons in it, and I've put 2 electrons in the 1 pi star. Okay. By the way, sometimes beginning students get confused about the G and U's and think G is good and U is bad. That's not the case. Don't think that. It's just symmetry. So in this case, notice that the good orbital, the bonding orbital, is a U, and the bad anti-bonding orbital is a G. So G and U don't mean G for good and U for bad. They just mean even or uneven. It depends on what orbital you're talking about, whether it's bonding or anti-bonding. So this one's bonding, but it's a U. Okay. Now, I've been kind of walking through this as if atoms have real atomic orbitals or actual atomic orbitals, and those atomic orbitals actually form diatomic molecular orbitals. All of these orbital ideas, I made the point at the beginning, are just mathematical constructs that are inspired by what happens in hydrogen atom. But these things aren't hydrogen atoms. So I want to remind you yet again that there's no such thing as an actual atomic orbital, except maybe in hydrogen. But what there really is mathematical inspiration from our thoughts about these pictures we've been drawing. And so we will use basis functions, which are atom-centered, usually Gaussian functions, inspired by this atomic orbital idea. And sometimes we'll even call the basis functions atomic orbitals to mean it's an orbital, it's a function of 1 electron, it sits on an atom, so in that sense, it's an atomic orbital. But basis functions are truly the fundamental objects. And we're going to use those to build our molecular orbitals, okay? So, and because our basis functions are just basis functions, I'm free to choose a lot of basis functions if I want, and that means I'll have many more of these so-called atomic orbital basis functions than what I've been showing you on the previous diagrams. And that's fine. Again, I'll form molecular orbitals out of these atomic orbitals, however many I have. If I have 1,000 atomic orbitals, I'll form 1,000 molecular orbitals. And that is fine. But again, I will fill the lowest energy ones first. So when I walked you through the diatomic molecular orbital diagram, that is a perfectly fine picture, but it's a picture appropriate to what you might call a minimal basis set, using the minimal number of atomic orbitals. But in a real quantum chemistry calculation, you might use double that number or quadruple that number of basis functions, and then that will entail having double or triple or quadruple the number of molecular orbitals, and those would, in principle, get plotted on some diagram. They'll have different energies, and the picture just looks way more complicated. So that's why I went with the minimal set in showing you that, and that's why that's what's in textbooks. What do you do for polyatomic molecules? Well, qualitatively, the procedure's all the same. You take atomic orbital basis functions, you form molecular orbitals, and you fill the lowest energy ones first, and you go up till you run out of electrons. So there's nothing qualitatively different. Are there simple diagrams for the molecular orbitals of polyatomic molecules? Yes and no. If they're sufficiently simple polyatomic and famous enough, like water, then yes, there are some qualitative MO diagrams. These are generally called Walsh diagrams, and you can find them in some textbooks. I'll show an example. But if you don't have something very simple like H2O, then don't worry about it. Don't try to go pour through the literature to find a MO diagram. Just do your own calculation, do a quantum chemistry Hartree-Fock calculation, and you'll get all the molecular orbitals, and you can plot them and put them on an energy scale if you want. You can see what they look like, and you can just make it yourself. And for anything but giant molecules, molecular orbital calculations are so quick and easy now with modern software, there's not a reason to not just do it. Unless, if you had some complicated inorganic or organometallic problem, it might be helpful if you knew rules of thumb like the 18 electron rule and some things, or how the d orbitals split in a crystal field in this particular problem, to have a bit of a clue as a user, are those electrons going to be unpaired or paired, and that helps you pick the spin. And spin's the topic of a future lecture, but it is connected to this particular point about the user having a bit of insight into the filling of orbitals is helpful in knowing if you have an unusual spin. So let me just show a picture of a Walsh diagram. This would be appropriate for something like H2O. A lot of times they show you the molecular orbitals as a function of some geometric coordinate, like a bending coordinate in HAH molecule. Here they say A because it's generic, so A could be, carbon or nitrogen or oxygen or something. It's a generic diagram. And you can see that I've got an orbital that's called A1 here, or it's called sigma G here. So these are symmetry labels, and once your molecule goes from bent to linear, the point group of the molecule changes, and I switch labels from C to V labels, A1 and B2 and B1, to linear labels like the ones we were talking about a minute ago for diatomics, sigma G, sigma U, pi U. So this tells you I've got a A1 orbital here, and then another A1, it's called a lone pair in this case, then a B2 and a B1, and I would, depending on what molecule this is, I would fill these up starting from the bottom and going up, and use the Aufbau principle to tell what my electron configuration was. This is interesting. There's a crossing of these two guys, and so depending on the angle, either this A1 is lower or this B2 is lower, and you'd have to know what angle you were at to know which orbital to fill. So that's kind of interesting. You can play a lot of games with these diagrams that I'm not going to get into right now. Finally, let me just make a concluding remark about hybrid orbitals. A lot of times these are taught in freshman chemistry, and rightly so, because if you're talking to a chemist will very frequently tell you this is an sp3 hybridized carbon. And it's good if you know what they mean when they say that, okay? So it's very valuable as part of the language of chemists to describe the bonding environment around an atom. That having been said, if you're a computational chemist, you don't need these things unless you're just trying to talk to your fellow chemist. In your calculation, they're totally irrelevant. Hybrid orbitals don't exist in a calculation. They're not needed, they're not used, they're not part of the calculation. Now, if you're a fan of hybrid orbitals, you can sometimes go back into a calculation and try to extract some ideas similar to hybrid orbitals. That's a thing, but just running a calculation, the basis set doesn't know about hybrid orbitals, the Hartree-Fock code doesn't know about hybrid orbitals. They're just not a thing in quantum chemistry except as an interpretation tool. Your molecular orbitals are built directly out of the atomic orbitals, and you do not take a detour through the realm of hybrid orbitals. That it just isn't a part of the calculation. So I know some people wonder about where hybrid orbitals go when you're running Hartree-Fock, and the answer is nowhere. They aren't there. But if you're a fan of hybrid orbitals, you can certainly extract some hybrid orbital type information out of a calculation after it's done. And that's all I have to say about orbitals and electron configuration. So I hope this is helpful information.